Oh, shit.
This is a 3D printed watertight high-pressure fuel tank.
No, it isn't.
What? Yes, it is.
That's just a prop you printed for the thumbnail.
Fine, you got me.
You're just copying the German engineer.
You made a good video, okay? Whatever. This is a 3D printed watertight high-pressure fuel tank, and in this video I'm going to show you how I made this 3D print stay watertight at pressures over 357 psi and potentially even higher. Right about now, you might be thinking to yourself, Space Cowboy, 3D print a fuel tank? Why would anyone do such a thing? To which I say, stop asking silly questions. And also because, science! I'm building a rocket engine, and not just any rocket engine. I'm building a pressure-fed rocket engine. A pressure-fed rocket engine uses liquid fuel, just like any other liquid rocket engine, only instead of using pumps to pull the fuel into the combustion chamber, a pressure-fed engine uses highly compressed gas to push the fuel from the tanks into the rocket engine. It's pretty simple in theory, but you might have already noticed that in order for this system to work, the fuel tanks have to withstand a higher pressure than the combustion chamber. So I have my work cut out for me building a fuel tank that can withstand higher pressures than the inside of a rocket engine. Normally, this type of fuel tank would be made from thick steel pipes welded together, or advanced carbon overwrapped pressure vessels. But I don't have carbon overwrapped pressure vessels, and while I can weld, I'd rather avoid going through the trouble of buying steel pipes and welding some caps onto them if I can. And what I do have is a 3D printer. So I'm going to try to 3D print this tank and see how it goes. But if any of you have ever tried to hold liquids inside of 3D prints, you might have noticed they're not exactly watertight. So for this to work, this print has to be 100% watertight since the fuel I'm using is alcohol-based and is 60% water by volume. On top of that, this tank will need to be completely corrosion resistant since alcohol can do some pretty funky things to 3D prints. As if all that weren't enough, it also has to be able to withstand some pretty high pressures. We're talking over 200 or even 300 psi. Just for reference, 200 psi is enough to put a hole straight through your hand if you're not careful. So let's get started. Now, this video was inspired by this other video by the German engineer, which itself was inspired by yet another video by SLPSTRM. In both of these awesome videos, these guys used a product called Dichtol AM Hydro. It's this really cool polymer that starts as a liquid, and you can inject it into your print or dunk your print into a bucket of it. You let it sit for a few hours, and the Dichtol penetrates through all the holes and pores and layers inside the walls of your 3D print. After letting it sit for a while, you end up with a watertight, smooth-walled print nearly every time. Well, that seems like a pretty good option, so I'll just do that. Problem: Dichtol is produced in Germany, and for some reason they don't ship to the US, and even Amazon can't magically teleport it to my front door. So I'm gonna need to find another option. To find a solution, I went to my lifelong source for unrefutably true, fact-based information: YouTube. And in my searching, I found this video, going over the results of a long, painstaking study into slicer settings to find the perfect watertight 3D print. So yeah, I'm just gonna copy that. So I hopped into my bamboo slicer and got to work. I set both the inside and outside faces to be 6 walls thick, with a 25% infill on a gyroid pattern. To make sure that this was a pore-free, watertight print, I lowered the layer height from 0.2 to 0.1 millimeters. And then for all of the inner walls, I increased the extrusion width to double what it was originally, up to 0.8 millimeters wide. I then increased the flow ratio to over 100% to try to make sure that that plastic just oozed together and melted all together. Then I slowed down the print speed for all of the walls and let it run. And the result is this: a 3D printed pressure tank that's so dense it could be used to fight off intruders, printed out of PETG instead of PLA because it's stronger, more resistant to corrosion, and more resistant to heat. And guess what you're going to get a lot of when you're testing a rocket engine? So I took my home defense pressure tank and connected it to a 6AN valve and fuel line system and added this pressure transducer so I could collect some pressure data. Now, you might be wondering, how am I going to pressure test this thing? 300 psi, where am I going to get that from? 2 words: pressure washer. So I bought this $100 pressure washer off of Amazon, and also got this fitting that transitions down from M22 to 6AN, so I could connect the pressure washer hose to my tank fuel line, just like this. Shit. So it looks like this M22 fitting actually just connects to a regular garden hose and not the pressure washer outlet. And that's not going to get the kind of pressure that I need. But not to worry, we do engineering here, and engineers find solutions. I noticed that these pressure washer nozzle tips all connect into the same quick disconnect fitting, and they all seem to be mostly hollow tubes up until the nozzle tip itself. So I took off the plastic, sawed off the nozzle end, and voila, a perfectly removable push fitting. So I brazed this onto my hose adapter, and bada bing bada boom, I have a pressure washer adapter. Now all I have to do is hook this thing up to a hose, turn it on, and see what pressures I can get up to before this thing breaks. A quick trip to my friend's house where they actually have a hose, and some silly pictures later, and I did just that. So that jerry-rigged connection wasn't great. Every time I would run the pressure washer, the push connection would come loose. I whipped out some good old-fashioned duct tape to hold the thing together, but then all the other fittings started leaking. Eventually I just taped the whole thing up, but I could only run the pressure washer for a few seconds before the water started leaking out of the tape too. I still recorded some data during the test, so I'm gonna go home and look over that and see what kinds of pressures we reached. Okay, wow. I honestly thought this test was essentially a failure, but I'm looking at these results and I'm honestly shocked. Let me remind you, this never got to high enough of a pressure to really test the limits of this tank, so it never faced any kind of damage. The walls didn't crack or leak any water, there isn't any water in the infill, the tank looks almost like no testing occurred at all. That's why I thought surely it never reached anywhere close to my goal operating pressure of 200 psi, right? Well, I was dead wrong, because we had consistent pressure readings hovering around 120 psi, with several peaks well over 250 psi. The highest pressure we read was actually over 357 psi. The fact I was able to reach pressures this high without so much as a scratch on the pressure tank itself is very promising. Obviously, I'll need to come up with a better fitting solution and run this test again without any leaks before I can safely use this on an actual rocket engine, but I think I'm actually onto something with this design. But I think we can do better. Okay, these compression fittings should make this a completely watertight connection now, but there's only one way to know for sure. Alright, here's the new setup. I've got my pressure washer right here, and running in the back of it instead of the garden hose, I have this diaphragm pump right here, fed by this Home Depot bucket full of water. This way I don't have to go keep using other people's garden hoses to run this test. I think it's pretty clever, and we'll see if we can get some data. Oops. Let's try that again. So that loud pop sound that you're hearing is actually that red metal fitting pulling straight out of the tank, completely stripping those 3D printed threads, which as far as I'm concerned is a connection failure, not an actual tank failure. So I still have some pretty high hopes for this tank, seeing that it still doesn't have any cracks or leaks in it. And the only thing that seemed to fail was the connection itself. But I'm going to go look through the data and see what kinds of pressures we got. I said we would do better, and better we did, to the tune of not just 300 or 400 or even 500 psi, but a full 1000 psi, which is actually just the maximum pressure that my sensor will measure. Now, there is the obvious elephant in the room that because of that thread failure at the end, we weren't able to measure these pressures over a long period of time like we would see during an engine test. But for a first prototype, maxing out the full range of my pressure sensor, I'm pretty happy with these results. But what do you think? Leave your thoughts in the comments below, and if you've ever thought about or done anything like this, let me know what you found out so we can compare notes. And for those of you who were wondering, yes, this design is airtight too. But that's a project for next time. Well, I think I'm going to end the video here, but stick around for future videos to watch this project come to life and see this tank design get used on a real rocket engine. If you're still here, thank you so much for watching, and consider subscribing. I'm basically brand new to this channel, so your support goes a long way. And hopefully, I'll see you next time.